Hello everyone, and welcome to video 4 on this Fundamentals of ROS2 with Python tutorial series. In this video, we're going to be covering an action, server, and clients. Now, if you stumbled upon this video and you don't know what's going on, we're talking about the robot operating system and how to use it with Python. Please go back to video 1 and see what the robot operating system is and what it can do for you. We're not going to go too in depth in this video, but just please go back to video 1 for that. On today's agenda, we're going to be discussing an example of an action client and server that we're going to implement, referencing some of the theory from before. We're going to, just like video 3 with the client and server, we're going to create an action package that hosts our data types. And then we're going to create a second package that hosts our client and server nodes, where we'll write those in Python. So this project is going to look very similar to the one in video 3, with very similar package architecture. So our directories are going to be very similar. And just like in what we started to see in video 3, if you're using the reference book, at this point, they kind of assume that you know what to do next with a lot of the steps on the command line and creating files and setting up your packages so that they run correctly. So they give you just enough and assume you know more. So one of the nice things with this video is we're going to fill in those gaps. If you got stuck following the book, then we'll be able to show you through this video what you may be missing. So just to recap, an action is similar to a client and server where you have a client requesting something be done. However, in terms of just requesting maybe some process data, you're actually requesting a goal to be achieved. And as part of needing a goal to be achieved, what separates a client and server from an action is that you need feedback throughout that service. And your goal succeeds when your feedback is that, your goal is met, but it can also fail, unlike just the client server service example that we provided in video 3. So an example that we're going to cover in this video is if you had a linear actuator, which, just fundamentals of robotics and actuator, in this case would be something that moves a component across a line. So that could be creating some kind of motion within our robot. And uh, that motion is going to be measured through a position. And we're going to be implementing a velocity to achieve that position. Now, when we do that, we're going to want some feedback throughout the process of moving the actuator to the desired position. Where is the actuator along the distance it needs to cover? That's going to be our feedback. And the output that we want is whether we met the position that we requested or if we failed in that action. So if the position was not achieved. And as we mentioned, something separating an action from just a service provided by a server clients is that you have different statuses that can be happening because of an action. You always have a pending status when it's just initializing, then it's executing, and our Python script in this case is actually running and doing what it's supposed to. We're getting feedback, and eventually, either one of these three things will happen. Either we'll succeed at the goal that we set out to accomplish with our action, and then our script will end. Second, we could manually cancel our action, and then the script will also end. Or third, the process could be aborted because some sort of error was um, present in the execution of this process. And so it just cannot meet the success criteria, and it also ends um, the script that's running. Before we get back into the simulator, just once again, please, this is the reference book that we're using. Please consider purchasing it to get access to the GitHub repo and reference code that we're using. For example, here's the GitHub, and here's the book where we could be um, grabbing some of the lines here. Um, you'll see me write a lot of this stuff in throughout this video, but please consider the book. There's a lot of great theory to read through that helps you understand what's going on. And you can grab a lot of what we're running on the Linux terminal or context for some of the scripts that we're creating or how packages are created and what we're doing. A lot of that context is present in the book, so please consider getting it. So as usual, I'm just going to enter my sandbox, the virtual environment, and like we mentioned, a lot of this is going to be similar to video 3. Just I'm gonna have some reference code up, but where once again, while this is loading, I'll just talk about it. We're going to create a package. It stores our data types. We'll talk about that, and then we'll just pick some of the package files so that we can actually successfully run that package and build it, set up our environmental variables, and then we'll create a second package to host the client and server nodes. And while this is loading, I'll just quickly mention that if you haven't already checked out the other aspects of the Construct AI, I really recommend them, especially going through those first 3 tutorial series if you haven't already. The Linux for robotics, C++, and Python, those are great starts. I'll probably create some videos on my YouTube channel about some of the necessary skills for that in case you want to see it in a different way or some of the additional details that might be missing from those videos. But they do a pretty great job and it's pretty hands-on, so I really recommend it. So I'm going to close the documentation. We're going to need our code editor and we're going to need a web shell, so a terminal. So I'm going to maximize my code editor. So you can see my packages. We have all the ones from the previous videos. And now I'm just going to go into the terminal and I'm going to go into my source folder as usual. So go into our workspace, go into our source folder, and we're going to create that first package we mentioned. If you watch video 3, this will look very familiar. So I'm just going to keep this command up in case you want to see it for a moment. We're creating this package called action underscore package. We're installing some dependencies through this line. So that ran successfully. I'm going to expand my terminal a bit so you can see it a little better. And now we have an action package. So the next thing, keeping that terminal open, we're going to go into the action package. And once again, very similar to our video 3, rather than making a services folder, we're going to make a directory or a folder called action, where we're going to store our action files, which are containing this .action at the end. So we need to go into that folder before we create our new action file. And you can do this through the IDE. I'm just doing it through the terminal, but we're going to create that action file. So going into our action package in the IDE, go into the action directory we just created, and here is our action file that we created through the terminal. Now I'm just going to grab the code for it from the GitHub. You can see it's pretty much just like video 3. We have our data types and some important data. So this is going to be a little different from the service file because we're not just providing an input and an output. These are all variables that we are concerned about in terms of understanding feedback and understanding how our action is doing while it's being executed. So we're going to provide it as an input, the initial position of the actuator. We're going to provide the goal that we want to achieve, and we're going to provide the velocity that we're going to move the actuator at to achieve that initial sorry, that goal position from the initial position. Now we're going to have this variable, which is a Boolean type called motion done. And what this is going to do is it's going to start false and turn true when we've achieved the goal. So this will be our success criteria. When this is true, then we're done. And finally, we're going to have another float value called distance that's going to be the delta value of our current position versus the goal. So essentially, where is the actuator currently versus the goal? How much distance do we have left to cover? So we're going to save this file. I'm just going to click Control S. You can also go to File, Save. And then before we move on, we need to go to CMake lists and add in something right here above element package. So let's go to CMake lists on the GitHub, and we're going to need to generate this interface so we can actually use our action file, the dependency we need. And then we're going to go to package XML, and we're going to grab these three dependencies that we need when building. And with that, we've completed this action package. So we just want to make sure everything builds well. So we're going to, in the last video, you saw me just go back to root and then go manually into workspace again. I just want to show this command as an option in the future. You can just do your tilde / so you're in root. Normally we would just do this to return to root immediately, but we can already get started writing, what directory do we want to move into next. So the CD command on Linux is pretty flexible, and you can see by doing that, I moved all the way back and then forward into the workspace. And then as usual, we're just going to run colon build, and that's going to get started building our new package. There we go. Takes a little bit of time. And still need to set up our environmental variables. But before we do that, I just want to talk about this warning that you get when running um, your colon build on this new package. And the reason we get this warning is because one of the dependencies that we added attempts to set up like it provides an interface for ROS to work with Rust. Now, we're not programming in Rust, we're programming in Python. So we can completely ignore this warning. It's not going to affect us. But this is just going to be one of the things to know about this workspace and the fact that we're using um, this particular version of ROS in our virtual environment. It's not meant to be used with Rust. So if you want to use Rust in the future, again, like C++ and Python are really going to be the two big languages that we use for robotics. But there is some interest in the robotics community to use Rust for security reasons. There's a lot of different organizations that are starting to move in that direction. I'm not going to talk about that too much here, but just know that you would have to use something other than ROS Humble, and or you'd have to install some fixes. You'd have to start to debug through that process. So thankfully, we're not using Rust in this tutorial series. We're just sticking with Python, so we can ignore this warning. And now that we built our packages, we're going to run our usual source install / setup bash to set up our environmental variables. And so now that those environmental variables are set up, we're just going to run this ROS2 interface show to just make sure that we can actually see our variables. And there we go. ROS can see our different variables that we set up. And everything seems set up well. This is a good cut check. Now we need to create the next package. So just like video 3, we had our action package, which reflects this service package. And now we're going to create the actual package to host our nodes, just like this service client _py package from video 3. So to do that, we need to go into the source folder to create a package. And then I'm just going to copy this code I have from here. And we're creating a package called linear motor control action with these dependencies. So now you'll see it here. And um, we need to go into it. I'm just going to type the same command twice because the name of the package is also the name of the folder inside of that package that has our node files in it. And from there, we can create our server file. And I'm also just going to go ahead and take the opportunity to create our client file as well. So now in this IDE, we can go to the linear motor control action folder inside of the package, and we can just actually open our servers and clients. I'm going to close some of these files at the top just to remove confusion. So those were in the other action underscore package. So now every file that I'm going to have open here is only going to be for this linear motor control action package. And once again, we need to go to get that code and we'll discuss it. So linear motor control action folder. Now let's grab the server file. So here we go. Here's our code. Do some of the usual imports. Something to know. We're importing from RCL Pi, that API that we talked about, so that ROS can use Python. We're going to import action server so we can actually create an action. And then from the action package that we created earlier in this video, we're going to import that linear control file from where we created our different variables and their data types. Because again, this is going to really look similar to the video 3 um, class that we created, where we're just creating a child class of superclass node. So it inherits from node. As usual, we're just initializing it, providing some of those variables that we created in our action package. We're giving it a name. We're running this method defined below, where we're initializing some of our variables. Then we're calculating that distance value. So our server, when it receives the request from the client, it initializes values. Then it calculates the current position, which is set up using the initial position, versus the goal position. So that's that delta we mentioned. And then we're just providing a rate at which we want it to continuously run and provide feedback. We're going to initialize our feedback message variable as the feedback from our action package linear control file. And then the main thing is this block right here. So you can change this distance value. Basically, it's saying while the distance is greater than this very small value, which should be 0, but we're not using 0 because um, we'd struggle to catch 0 as a value in code. So this very small value is used instead. So while the distance, how far away is our motor from its target value, is greater than a value equals to 0, we're going to continuously check, where it is. So we're going to update the motor position value by using this function, just essentially calculating the previous position plus the velocity times a new step, which this is just one of the basic kinematic equations from physics. Um, that's VF equals VI. Wait, no, it's fine. Well, velocity is just dx over dt, and we're multiplying it by a delta t. So that gives us just a change in x, and then we're adding that to our current x. So that's our kinematic equation. And we're also just adding this else clause in case we go under zero into negative values, we can handle that situation. And finally, we're going to provide that as feedback, and we're going to publish that feedback. And it's going to continuously run this loop until this condition is met. So until the distance is less than this value, which is very small. And the reason that, again, zero is difficult to catch is because it has to be less than that value. So we're asking for quite a bit of precision here. And then we're going to, when that while loop is concluded and that this condition is met, we're just going to announce that the success criteria has been met. We're going to provide our results so that we can return that. And we're going to set motion done, which is that variable that marks that the success criteria was met, to true. We're just going to return, and all of that is called here in our main function. Once again, we're just initializing an object of class linear control server, which when that happens, because of this init method, we're actually running this entire method below. So once that initializes, all of this stuff is run. And then we're just running our API command spin so that we can see this occurring across the ROS network. So that concludes our server. Now let's discuss our clients. So we'd go to grab that code from the GitHub. Oops, I did not mean to download that. And then we just let me just make sure I got, okay, yeah, there we go. So similar to the server, just importing in a lot of the dependencies we need. Similar to the server, we're referencing our API so that it can handle built-in action clients. And then we're also referencing that action package we created earlier, where we have our action file linear control that hosts the data types of our different important variables. Now, once again, like a lot of this is just going to start to be repeated and look very familiar throughout these video tutorials. We're creating a child class of superclass node, so we're inheriting from node. Then we're just rewriting our initializer so that we can initialize this client to have some of those data types. So this kind of looks like the client from video 3. We're just giving it a name. And then we're going to provide several methods where this send goal method actually sends the server a request. We're going to provide several initializations of variables with that, some of the parameters of this method. So we could set up the initial position, goal position, and linear velocity to do different things, and you can play around with that. And so then with that, like we mentioned in the PowerPoint, let's just go back to that briefly. We have different action statuses, and those are going to be reflected here, where first we need to wait for the server. So there's that pending status. We're going to wait for both the server to be discovered and then for our first bit of feedback to be provided so that we know that we can continue to execute. And within this feedback, we're going to be running some of these methods from below. So feedback callback is going to check whether we received feedback from the server. And when that happens, we know that we're in the execution mode of the action so that we can continue to receive feedback until one of the 3 end criteria is met. So then either we succeed at our goal, we terminate the action ourselves, or some kind of error occurs and automatically ends the process. And so when that occurs and we get that callback for, okay, feedback is good to go, we're executing, then we're starting to run our main method, which is a mix of these two methods. Goal request callback, which is present right here as the parameter that we're passing in. And then this get request callback is part of that goal request callback method. Now, in order to do this, we're just looking for results. So referencing some of our prior code. And like we mentioned, if um, the goal is not, and like we have some exit criteria, either we're gonna get an error and exit programmatically because our goal value is not valid, so then it'll be rejected, or we'll continue because the goal is valid and we'll kind of log that as the goal being accepted. And then we'll just continuously call back to get, with these lines, we'll continuously check feedback, you know, publish that feedback through the ROS network, and our server will handle whether, how is this process doing? Do we achieve the success criteria? But we're just continuously checking that at this point. And then when it's done, we'll run this get result callback. We'll print out the final result. So the success criteria was met. What was the result of that? And we'll run our shutdown to um, kind of conserve some resources. And all of that can be seen, you know, all of that gets abstracted out in our actual algorithm where we're just running a lot of the standard initialization, creating an object of our class that we defined above, setting up some of our variables. So this is the variables that you can play around with. What is the initial position of the motor or actuator? What is the goal position that you want? And what is the velocity you want to achieve that with? And we're going to just run our send goal command. So when we initialized, the data types are set up. When we run the send goal command, all of our different methods are run so that we're checking, you know, our pending status. When we confirm feedback is received, we move to our executing status. When we execute long enough that one of the end criteria is met, then we terminate the program and we know that the motor is at the right position. And once again, we're just running the spin command so that we can continuously discover this process through the ROS network. So that's our clients. Um, and don't forget that we need to set up our setup file to actually be able to use those files. So just going to quickly grab that code here. This is one of those things among several things we've skipped over that they don't tell you in the book anymore because they just assume that you can do it. Oops, and I'm just going to include the client one by rewriting it here. Clients. So that when we run ROS run, we just reference it all as server, and it knows that it's talking about that that server.py client.py file in the directory. Great. So now that we've set that all up, we can go back to our terminal and we can go back to our workspace. We can run colcon builds. And with this, we'll build out our new package with our new nodes. We'll run source install setup.bash. And I'm just going to grab the ROS2 run for the server. So we're making sure we're going into that package and running our server node. And then, just like usual, while that's running, we go to another terminal because our server is taking up that terminal. And now we need another terminal to run our clients. Space. And then we're going to run, we already built our package, so we don't need to rerun colcon build. We're just going to run source install setup.bash so we can set up those environmental variables. And then I'm just going to quickly grab the client one. And here you can see it going. So we receive feedback Um, it's pretty quick because of the time rate that we set up. But you'll see essentially every few milliseconds, we receive feedback on the position, we receive feedback on the position, and eventually we go from just kind of scrolling up to the top, um, right after our goal is accepted, and we move from the um, pending to execution phase. We're starting at our position, which was 0, and the distance, which is the received feedback, is from 0 to 1.7. Our initial delta is close to that. And as the velocity moves it, the linear actuator across that distance gets reduced, 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 all the way down all that feedback we received, down to that near 0 value that we wanted, which we set up the precision. We can change that if we'd like. And eventually, when our success criteria was met, then we receive this result true. Now, that concludes our server and and clients in our action package. However, if you want to play around with these values to just kind of see how that affects uh, the execution of this, I recommend that. You could change this velocity, set it up to a really high value, set it up to a really low value, change your goal position, change your initial position. Also going to the server, we can change our rates and set up um, our time scale so that our time step, my bad, so that this we get feedback in a different amount of milliseconds every trial. So you can change that value to play around and just kind of see how that affects our code. And if you're a little more savvy with just robotics in general or engineering, control systems, you'll notice that, we have a very basic control scheme. So just as a little bit of added value to this video, we're kind of just checking a criteria with feedback, but we're not really changing our um, our velocity, our acceleration. We're not measuring our error over time. So what I'm getting at is this isn't the best way to achieve this goal. As a roboticist, you might implement something like a PID controller to either, one of many things can happen with that. You can achieve your goal more efficiently, so you don't oscillate around your value of, you know, trying to get to that zero, like that close to 0 value. You're not oscillating in above it and below it, then above it, then below it, and that might take a while. Um, there's a lot you can do with some more advanced controllers, and we'll talk about that to not only achieve the motion in a more controlled fashion, so um, we can achieve a nice curve towards approaching our final desired value. But also we can do that in a more quick, more efficient way. So not just improving precision, but also you know, the efficiency of how we actually get there. PID control is a bit outside of the scope of this video and this fundamentals tutorial series. But in the future, just so you know, I do plan on releasing some more advanced videos on ROS. And as part of that, we'll talk about ROS2 control, where we can actually implement a PID controller. And then you can go back to this video and potentially implement that. So thank you for watching. Um, In the next video, we're just going to conclude this section on the communication schemes for ROS. So that was the publisher subscriber, client server, and the action. We're going to conclude that by talking about custom messages that you can stream over your ROS network. And then we'll move on to another subject beyond that. I'll see you then.